So you will notice when you look around on this floor that there are some beams that are traditional structural steel and then some that are the D-beams. The D-beams are going to be right here through this corridor on both sides of the column lines, and the bottom flange is just fire protected. Only in areas where they need to achieve that 8-foot 8-inch or well, I guess they're doing 10-foot floor to ceilings on this project, do they have those D-beams. There may be situations, possibly right here, where you see a deep, full depth structural steel member where there is something else going on where they don't have a clearance issue. So for the most part, the D-beams are only where you really truly need that clearance issue. As he mentioned in his presentation, the span of the D-beam is really like 18-foot max, 17.6, something like that. And that's really just because when you open up a girder slab design guide, there's really only 6 to 8 approved sections. It's not something that you can take any wide flange section and optimize to go 30 feet or anything like that. So when you're left with that limitation, you have to be able to get longer spans because of the parking down below. There's no way you could do a parking with an 18-foot drive lane. So what they did here, and you'll see, is those are the kickers that we were talking about before, where you have the kickers that are a knee brace, essentially back up, and at the end of the kicker they have essentially a splice to the D-beam, and that kicker is then connected back to that column tree. So the column, for the most part, is prefabricated with that stub on it, and then in the job, when they were setting the steel, they connected it back to that splice. So now they are able to add on about 2 feet on each end to get to 22'6" to accommodate the parking requirements down below. So also you'll notice that you're going to see traditional steel anytime where you see the lateral force resisting system. So you see your eccentrically braced frames back here. The D-beams are not taking any of the lateral load. And also on the perimeter of your structure, the D-beams need to be loaded on both sides. It's not a good idea to only put your precast hollow core plank on one side of the D-beam because it's not torsionally resistant anymore. So you want to load it on both sides. So usually on every time on the perimeter, you have that part of your facade and you just use a traditional steel. So you're going to have a different top of steel elevation between your D-beams and your conventional steel because of where the plank is sitting at. They've got these tube sections that are attached to the outside column flanges where they have their bearing points. And you'll also notice there's no perimeter steel in the long direction. That's something Matt was talking about. It's pretty unique. So there's no perimeter steel, so that helps the fact that if there's an architect that's wanting floor to ceiling windows, you're designing that outside plank member as a solid core usually. So there's no core, it's a solid plank that's designed for those intermittent attachment loads possibly. Here it looks like they're spanning column to column, but for the most part, if you are going to attach to that exterior plank, it's going to be a special type plank element. So the plank is sitting on the bottom flange of the D-beam. So this is the top flange of the D-beam, and the bottom flange is much wider. So they'll lay the plank down and they take a sledge and they're actually, well, they cut it and they break it out so they have holes in their plank. And then they'll come back through and grout that. So they're grouting a section that's probably about 6 foot back through here, through the opening of the D-beam and through it. And I haven't seen the structural details, but sometimes there's a reinforcement bar that's also aiding in that composite action. So they do this continuously. And this is one of the main reasons that you do need a leveling compound on there, because this is not the perfect pristine finish that you would expect as compared to just traditional plank that's been extruded. So, and these are just lifting lugs for lifting the plank. So here in Chicago, it's common to use 8-foot plank. A lot of areas around the country, you'll see 4-foot plank. It really depends on the plank supplier, but this is how they hoist the plank into place. If it's 4-foot plank, sometimes they just put a sling around it, but with 8-foot plank, this is what you typically see. So this is a piece, 8-foot section, 8 foot wide, so there's 2 on each end. This is another plank here. So that's appropriate to those, and those are for that plank. You can kind of feel they have like a clamp on it. On the East Coast, they have like these vacuum suction things that they'll just grab onto the plank and lift them up. But this is typical what you see in Chicago. All right, guys, on this floor, you're gonna definitely see the introduction of how the rooms are gonna be laid out. And this is important, particularly those of you who are structural engineers, to understand and appreciate why and how all of this works together. There's a reason that they use D-beams, and it's because of, for example, this hallway clearance right here. That if they had to use a traditional deep section, just like this guy, you'd be protruding down another 12 inches possibly, and that would be a problem with getting that clearance that they need. So as soon as a floor or two has composite action, which means all the seams have been grouted and it's a structurally sound floor, the other trades can come in and start quickly working. So you'll see mechanical, electrical piping happening, you're gonna see bathroom workings, you're gonna start seeing all of this happening, and maybe on the lower levels we may see a little bit of drywall, I don't remember. But that's quickly how they work. And the faster the steel guy can get in and out, the quicker this turnaround can be on the other floors, which obviously leads to quicker occupancy and the more generation the owner can gain quicker. As you can see here, here's a kicker brace coming down, and it's actually part of a demising wall. So this is where it works. There's going to be applications where you will notice that that kicker is actually out in the open, which means it's not a kicker, it's a moment connection. Those are those 4 locations on each floor he mentioned where you actually cannot use the kicker. So that's where there's no wall and they had to have a more expensive moment connection. So this plank is grouted with, so the diaphragm, as they're assembling this, they have weld tabs on the end of the plank. And they do. It's like more of constructability. So they're weld tabs, so as they set the plank, they have weld tabs that come with it, and they're welding it to the, like, tacking along the bottom flange of the D-beam. And then they come back and they grout all of the seams of the plank.
Right, okay.
So once that's grouted and the grouting has cured, then this entire floor is the continuous diaphragm. So this is attached to the 2 end bracing systems that they have here. So as the wind blows, it applies to the floor. The floor is the diaphragm that gets it back to those lateral systems, and then it chases its way back down. So the taller structure you have, the diaphragm loads won't be able to make it through this thickness of plank, and that's where you start seeing where they'll add on like 2 inches of structural topping or 3 inches of structural topping. So you'll see a high-rise building that's like maybe a 30-story building, and there's no way, because those lateral loads just keep chasing down, and particularly like a staggered truss where it's not a consistent brace, it's a brace every other floor. They go in the lateral system, they chase back out through the diaphragm, and they keep going and zigzagging back and forth. On the bottom floors, the floor system will be really thick because it's all those accumulated diaphragm loads from the whole structure height down. So yeah.